Hi, my name is William. This is my Fluent project. So to set up a simulation, you're going to want to click here, double click here, set this geometry to 2D, and that's all good. Double click here, wait for it to load. Once you get here, you're going to select the Z-axis to face you, and then you're going to go over here to sketch rectangle. Start from origin. Dimensions. Each side. Horizontal. Change the units to linear. Set the height here, or the horizontal length to 150, and height to 10 for whistle flow. And you're going to get here. And we're going to go to surfaces from sketches. Select apply to this whole thing. Just select the whole thing. Select apply, then generate. Then you have your wall here, and then you're gonna go to edge. We're gonna name all the sides. Alright. Edge. Press N. Select this. Press N. Alright. Once you're done with this, we're going to close out this portion, and now we can work on our mesh. Okay, so we're going to name our edges. So for this one, we're going to call this the top wall, bottom wall, inlet, and our outlet. Alright, now we can work on our mesh. So we're just going to right click, insert, sizing. Then we're going to select the upper and the lower wall. Apply. Change element size to number of divisions. This 150. And also change behavior to hard. And then you're going to do it for each side. So for this one, for the inlet. Size. Then you're going to generate. It's going to take a little bit. Once that's done loading, you're going to get a funky looking mesh here. So we're going to go ahead and clean this up by going to face meshing. Select apply and generate. That's going to take a little bit. I'll go back to you. That was quick. Now we have this. So the next step is to this is our mesh, so we're going to go back to the mesh. Update this. It'll become a green check mark. Okay. Click on double precision. Oh, here we go. Okay, now we're going to wait for the results to come up. So we need to load, jump to that. Alright, once it loads, the first thing we're going to do is go to results, residuals, and set these criteria to actually, we're going to set our mediums first. So we're going to materials, flow, layer. And make sure you set under models, this SSTK Omega to lambda. Hit OK. Go to residuals. That looks good. Alright. Materials, air. We're going to change our density to 1. For viscosity, to the number 5. Change create cutouts. Go down to reference values. Compute from the inlet. Surface body, everything's updated. This is good. Our boundary conditions is where we change the variables for the system. For this case, we're going to change the inlet velocity to 0.04 meters per second. calculate this number, and to create Reynolds number, you get a number around 2000, which is laminar and not turbulent. Click apply, close. To the outlet pressure, make sure to prevent reverse flow. Apply, close. Make sure the upper and lower walls are stationary with no slip condition. Good. From here, we're going to double check the reference values. Looks good. Now we're going to scroll down to initialize and click initialize. Initialization is done. Once it gets done loading, you're going to go to run calculation. Change the number of iterations to do 150. Then hit calculate. Alright, so once it's loaded, you're going to set it to face the z-axis and click location, line. We're going to have the midline. Set this to 0.75, 0.01, 100 samples. Click apply. For the next line, we're going to do endpoint, or end line. This one will be 150 or 149. Just so that we get the data. Then the number snaps to 100 again. This is also so you can read data where you want to read it. Alright, and then click apply. You can also add a line for the developing fluid. That or developing flow. And this one will be there we go. This one will be a little bit in front of the inlet, just before the actual flow has developed. Click apply. Then, it's a little too far, I think. I'll go ahead and set this to like 1. It's better. Then once that's done, you're going to go to contour. Create a contour for the symmetry 1. And then instead of pressure, we're going to go to velocity U with 110 contours. Then click apply. And you can see here our flow. Then you're going to go to this label here needs to go to the side. Let's go fixed and horizontal. There we go. And then you're going to go to ease. For the developing flow, we're going to set this to once the legend is out of the way of this, we're going to go to chart, create a chart. For the data series, well, for the chart title, we're going to change it to velocity profile for Oiso flow. And then data series, we're going to change this to midline. Location of midline. Then for the inline, and the developing flow. This will be the developing region. At the developing flow. Then you're going to change the x-axis to velocity u and the y-axis to y. Click apply. Then you're going to get a result like this. You can see that it is laminar, since it looks very smooth. And at the developing point, you can see that it is a little faster on the outer edges, a little slower in the middle. That's because it needs time to develop its flow, to have the highest flow in the middle. This is due to the shear viscosity of the fluid, or I guess shear modulus of the fluid. Right, you got a stationary surface here and a constantly shearing material, where the least amount of resistance is in the middle, so it'll be the fastest. And we can see here that in chart viewer, the blue line represents the end line and then the red line represents the midline, but they overlap each other, which means that they're the same, right? So in the midline and the end line, the flow characteristics are the same. Then once you're done with that, you can export your data, and then you can examine that for this particular flow. And that is that for Poisson flow. We're going to move on to the other flow, the Coet flow. So for these particular values of density of 1 kilogram per meter cubed, viscosity of 1e negative 5 kilograms over meter seconds, and inlet velocity of 0.04 meters per second and a total length of 150 millimeters, comes out to about a Reynolds number of 600, which is considered laminar. So this checks out. Messed up. The midline wasn't showing. I had this descent set to 0.75. It was supposed to be 0.075. But now that I got it corrected, Now our data is here in the midline, and as you can see, there's a little bit of red showing, so it's perfectly right underneath. So now I'm going to export this data to this one, overwrite, exit, export, overwrite, and now we have the midline data for that as well. Alright, for our co-ed flow, we have basically the same setup with the geometry and the mesh, except the geometry, the height is 5 millimeters instead of 10. The same number of segments for the height as well, for the height and the length for the mesh, and the length is obviously 150 millimeters. But for the setup, I have changed a couple of the parameters. So everything else up here is the same. I made sure this is changed to laminar. For the fluid, however, for the air, I'm going to change the viscosity to 1/1000th instead of 1e -5. So confirm that. Make sure this is on air. Yep. And the key difference is for the inlet, for our boundary conditions, the inlet velocity will be 0. Now for a co-ed flow, we're going to change the inlet condition to from a velocity inlet to a pressure inlet, and we're going to prevent the reverse flow. Make sure the prevent reverse flow is also selected for the outlet. Now the key difference here is that our wall conditions will be a little different. So for the bottom wall, it'll remain stationary with no slip. For our top wall, however, we're going to change this from stationary to a moving wall at a speed of, say, like maybe 6. We'll just guess 6, and then we'll see what our Reynolds number comes out to be. Alright, click apply. Now we're going to check our residuals, make sure these are right. Yep. Oh, actually, let me change this to .06. Change this for all of them. That's good. Make sure it is getting your reference values from the inlet, not from the surface body at the inlet. Now we're going to go to initialization, and we're going to make sure, yep, everything's right, and initialize. Gonna wait for this to load. Alright, so once this is initialized, you're gonna go ahead and run the calculation. I'm gonna make the number of iterations to 200, and gonna click calculate and wait for this to finish doing its thing. Alright, our calculation is complete. So we're going to go back to our workbench and double click the results. Okay, so in our results page we pretty much have the same setup of our midline, endline, and developing flow line. As you can see, I just made the this half of a value just to be more precise. So 100 apply. So as you can see, our velocity U, we have really good shear, and it looks laminar. We will calculate the our Reynolds number to be sure. Let me do that real quick. So we're gonna go ahead and go to create a chart for our data series. We'll title it co-ed flow for our two series. We're going to have midline 1, we're going to have the midline and have this location and end line. So we'll hit apply. Oh, we're gonna hit the x-axis. We got velocity, and the y-axis we got y. Hit apply. They're sort of overlapping. Let's see. Alright, so for my setup, I changed the velocity of the top plate from 6 to 8, and that made this look a lot better. So yeah, I think I'm gonna stick with that for the results. See if I delete midline, it shows my endline, right? 145. All domains apply. Data series midline. Oh, there we go. So they are clearly overlapping each other. As you can see, if I apply the midline, it's right there. So, and doing the calculation, the Reynolds number comes out to, yeah, so we get 1200 for our Reynolds number for these specific parameters, and that is why we get such a nice line here. Same flow with our end line and midline. And this is our gradient for our flow here. Looks nice. You see like a clear, steady consistency. I'm not seeing, yeah, almost no difference in the for each y-axis change. It's relative to the x. There's no change. So now we're gonna export the data so we can evaluate it further. that was it for co-ed flow. So for hybrid flow, it's pretty much the same setup. The geometry and mesh, I pretty much have it the same. But for the setup, it's gonna be, I just combine for the boundary conditions a inlet velocity and also a translation of the upper wall so that it becomes a hybrid flow. And then for the results, as you can see, I pretty much have it set up the same with the end line, midline, and developing flow. You can see how the velocities behave now with inlet velocity and with a shearing action. And for the chart, we have sort of a cutoff. So this is where the plate is moving. So the liquid has a velocity by itself, but at the bottom, the velocities closes off. And so as you get towards the middle, it's still increasing when you go above the middle to a certain point. So this is the height at which the fluid reaches the maximum velocity, 0.003 meters. So it all checks out here. And then I added some vectors too to sort of visualize the flow. And yeah, that's pretty much it. So my Reynolds number was a little high, so I'm turning down the viscosity by half. So I changed it from 0.0001 to 0.0005. So save this. Now for the top wall, you can see the speed is at 0.6 meters per second. And then bottom wall stationary, no slip. The outlet should prevent reverse flow. Inlet, good, 0.8. So just gonna initialize, boom, and run the calculation, 200 iterations, and calculate. So give this some time. Alright, calculation complete. Exit this. See what our results are. Refresh. Let's see. There we go. Now it's changed a little bit. Yeah, it looks better. From what I see here, it looks pretty smooth, so I'm happy with that. Looks like the Reynolds number is gonna be, it's pretty close. My Reynolds number is 2100. I'm happy with that. It's less than 2500. So that's pretty much it for the hybrid flow. Yeah, I'm happy with learning.